Lemma 6.10.5 next, where as usual T is a linear operator on a finite dimensional inner product space V. We have to prove that T is unitary if and only if T star equals 1. That means the product of T and its Hermitian adjoint equals the identity operator. So the proof of course is going to have two halves because it's an if and only if statement. Say in this half we assume that T is unitary and then we need to prove that this happens. Then for any two vectors u and v in our vector space V, we consider this inner product of u and the T star image of V. By the definition of product of two operators, T star is T star. That means this is the T star image of Vt. But then you know what you can do once you have star here, star of an operator. You can move that operator over to the first component. Then the operator would lose star. That means T star will become T. So that way you are getting ut, Vt. Now you use your hypothesis that T is unitary. So the inner product of ut and Vt will be equal to the inner product of u and v. And the fact that this equals this implies that this Vtt star has to be equal to V. Now because this is true for any V belonging to V, so this is the identity operator. However, what is not immediately clear is how exactly this thing implies this. To understand how, you see this. So in this part we have shown that the inner product of u and Vtt star is equal to the inner product of u and v. So that means this minus this is equal to 0. And then using linearity, the left hand side becomes this, the inner product of u and Vtt star minus v, that is equal to 0. But note also that this is 0 for all u belonging to v. For any vector u in v, this is 0. In particular, in place of u, you can take this itself because that is also after all a vector in v, and get this fact that the inner product of this vector with itself is 0. That means it is orthogonal to itself. But the only vector in an inner product space that is orthogonal to itself is the 0 vector. And that comes from the definition of inner product itself. So that's how this becomes 0. And from there we are getting this. So that is one half of the proof. The converse part also actually uses the exact same calculation, just interpreted in a slightly different way, because the hypothesis here in the converse part is the conclusion here. That means now we are starting with this. This is our hypothesis that T star is equal to 1. Then for any two vectors u and v in V, this time we consider this one. That means we start with this one. The inner product of u and v is equal to the inner product of u and v T star. And that is because this is the identity transformation. So the T star image of v is just v. So it's coming from there. And then the calculation proceeds exactly like these steps. This first becomes this, and then the T star moves over to the first component becomes T, and that way you get ut, Vt. But then this is the meaning of an operator being unitary. So that is how T is unitary, and the proof ends. And from this lemma we can further draw this conclusion. So a unitary operator is non-singular, because if T is unitary then this happens. So that means T has a right inverse, and with its inverse equal to its Hermitian adjoint. We are straight away saying that it has an inverse. However, how do you know that? This equation only tells us that T has a right inverse, which is its Hermitian adjoint T star. What about its left inverse? Does it then also have a left inverse? Yes. and that follows from corollary 3 to theorem 612. If you go back, there you would see that we proved a general result. It tells us that if you have an operator on a finite dimensional vector space, need not even be an inner product space, which has a right inverse, then it also must have a left inverse, and the left and right inverses have to be the same, and so the operator would be non-singular. So from there we are getting this fact actually, that if T is unitary, then this happens by this lemma, and that is why via this corollary T becomes non-singular and its inverse is just its Hermitian adjoint. Next, theorem 610(2). Suppose you have a finite dimensional inner product space again, because that's what we are considering here, which has this orthonormal basis consisting of these n vectors vi, and say we have an operator T on V, and in this basis the matrix of T is this n by n matrix. You understand that it's an n by n matrix where the ith row jth column entry is alpha ij. Then the matrix of the Hermitian adjoint of T in that same basis is this n by n matrix with the ith row jth column entry beta ij, where beta ij is the complex conjugate of alpha ji. If you already know about Hermitian adjoint of matrices from matrix algebra, then this is the source of that definition. Looking at this, you will see why. The proof starts by considering the matrices. Because T and T star have these matrices respectively in that given basis, so we have these two equations which actually are not just two equations. There are two n equations here. Two equations corresponding to each value of I, and it's understood that I varies from 1 to n. In that sense, we have written this. Ideally, we should have also written the variation of I here, 1 less than or equal to I less than or equal to n, but that's understood. And this is something that you already know. I mean, although we have written the equations here as if they are coming from these matrices, but it's the other way around. These equations come first, and then by looking at these coefficients, we form the matrices. So although you know it, but still let's just see what it is. So that means you are applying the operator T on the basis vector Vi, then it's again a vector in our vector space, so it will be a linear combination of those same basis vectors. This specific linear combination where the coefficient of the basis vector Vj is alpha ij and j varies from 1 to n. So like that, if you write all the n equations and there you look at the coefficients, then the coefficients in the first equation become the first row of this matrix. The coefficients in the second equation become the second row of the matrix, like that. Similarly, Vit star is summation beta ij Vj, because this is the matrix of T star where j varies from 1 to n. Okay. And then next we straight away consider beta ij. Now you go back to the theory of inner product spaces, and there you see that if you have a vector expressed as a linear combination of orthonormal basis vectors, then the coefficient, for example here beta ij of Vj equals the inner product of that vector with Vj. In fact, in the latest video on vector algebra that we did, we studied components of a vector. There, however, vector means the vector that you know from physics. These are generalizations of physical vectors, but they also follow the same pattern. So there we saw at one point in the video, if you go back and see the vector algebra video, the latest one, where we studied components of vectors in the direction of unit vectors. There we saw that if we have a general basis set, consisting of non-coplanar vectors, and you have a vector expressed as a linear combination of those non-coplanar vectors, then the coefficients are not necessarily the components of that vector in the direction of these non-coplanar vectors. However, if it's an orthonormal basis set, then they are. It's that exact same thing here. But anyway, so now we have this. And then what do? You can push this T star over to that side. It becomes what? It becomes T star star. Then from one of the properties of Hermitian adjoint, that is equal to T. And then here we use this equation, carefully noting that now we have J here instead of I. So for the other index, I use another name, K. So this becomes summation alpha jk vk. So I have written K in place of J and J in place of I, where K varies from 1 to n. And then we use conjugate linearity to push this Vi inside this sum. There is one more line that you can write here. So in that line what you write, summation inner product of Vi and alpha jk vk, and then using conjugate linearity that alpha jk comes out of the inner product. Because it comes out from the second component, it does not itself come out, but rather its complex conjugate comes out. So that's how you have alpha jk bar. Okay, and now you look at this sum. Because the Vi's form an orthonormal basis, these inner products are either 0 or 1. You can think of these Vi's as your physical vectors I hat, j hat, k hat, like that, in 3-dimensional space. They are unit vectors in the sense that their norms are equal to 1 and they are also mutually perpendicular. So this inner product will be 1 precisely when Vi and Vk are the same. That means I is equal to k. The other inner products will be 0. So that means in this sum, only one term survives, which corresponds to k equal to I. So that is how you are having alpha ji bar times 1 you have here, which however vanishes. So that's it, that's what we wanted to show. Beta ij is equal to alpha ji bar. And from that theorem we get this situation, these equivalences. T is unitary if and only if T star is equal to 1. We saw there in that lemma. If and only if. Next we write things in terms of matrices. Because matrix algebra and operator algebra are isomorphic, this happens if and only if the product of the matrices for T and T star equals I, where I is the n by n identity matrix. What does that mean? To multiply these two matrices, the ith row jth column entry of the product matrix by definition of matrix multiplication is this summation alpha ik beta kj, where k goes from 1 to n. That should be equal to the identity matrix, which means that the diagonal entries will be 1 and the off diagonal entries will be 0, and that corresponds to this. I not being equal to j means the I, jth entry is an off diagonal entry, so that is 0, and this is the diagonal entry. If I is equal to j, that should be 1. But the theorem provides us with these betas. It tells us exactly what these betas are. So in place of beta kj, you can write alpha jk bar complex conjugate. So that should be equal to 0 if I is not equal to j. However, if I is equal to j, then in place of alpha jk bar, you will just have alpha ik bar. So here you are having alpha ik times alpha ik bar, which equals the square of the absolute value of alpha ik. That is equal to 1. So T is unitary if and only if this happens and this happens. What are these? These are equations telling us something about the entries of the matrix of T. Let's end the video next with this natural definition, which comes naturally having considered Hermitian adjoints. If T is an operator, then T is called self-adjoint or Hermitian if it equals its Hermitian adjoint. If, however, T equals the negative of its Hermitian adjoint, or the same thing, that the Hermitian adjoint equals minus T, then we say that T is skew Hermitian. This is the type of operators that is usually used in quantum mechanics. Actually, this is what happens. You have a quantum system and its state at a given time is given by a vector, which is a vector in some Hilbert space. Hilbert spaces normally are not finite dimensional. I mean, there are finite dimensional Hilbert spaces, but the type of Hilbert spaces we use in quantum mechanics are typically not finite dimensional. But on those spaces, we have self-adjoint operators. And eigenvalues of these operators, or characteristic roots, whatever you want to call them, they tell us hidden things about the quantum system. So eventually when we go to quantum mechanics, we will see what these things are and how these things are, not exactly these things, but their infinite dimensional versions are used.